All right, so we'll get started. On Monday, I left off, and I didn't cover all of my slides on Monday. Okay, so on Monday I got as far as my computer's having trouble opening it. I didn't cover the last section on the bias variance trade-off, but you know what I want to do is I want to be able to start the next topic, and so I think I'm going to record a separate video on bias variance trade-off. I'll record that and I'll post it, and I'll have you guys watch that. And I'll just kind of talk about these last few slides that I didn't talk about in Monday's lecture. It's just kind of a neat illustration of how bias variance trade-off works. But I left that out on Monday, so that'll be a separate video for you to watch. Okay. All right. So today, what we're going to do is we are going to I'm going to introduce neural networks. Okay. And it's an exciting topic. Each year when I talk about, have you heard of neural networks? More and more students are saying yes. Okay. So I think by now, if I asked, have you heard of neural networks? I imagine most of you have at least heard of it, have at least heard of a neural network. Maybe you don't know quite how it works, but you've at least heard of them. And so we're going to introduce at least the most basic form of a neural network. Before we do that, I want to just kind of review gradient descent, because gradient descent is going to be what we're going to use to train our neural networks, okay? And I guess we're not even going to get to the gradient descent part today, but if you recall, how gradient descent works is that you've got some function, okay? The function depends on some value w, all right? So maybe it's our loss function, and it depends on your current estimates of slope and intercept. And what we want is we want to find the slope and intercept that will minimize the loss function, okay? And the way it's going to work is, rather than taking the gradient and trying to set it equal to 0 and solve, what we're going to do is we're going to take the gradient and we're going to apply it iteratively, right? And so we might start at some arbitrary location, w at time 0, and we want to know, well, what is w going to be at time 1? And so if you remember how this works, the answer is you take w at time n, and you're going to subtract off gamma times the gradient of f at w time n. So you take the gradient at your current location, w sub n, and you're going to just take your current value of w sub n, and you're going to subtract off some constant times the gradient, okay? And this constant gamma can be anything from any positive number, okay? Any positive number. So as long as it's bigger than 0, it can be that. So it can be a really small number. It can be a really big number. We saw, a little bit of the effects, or at least I tried to show a little bit of the effects of having different gamma values. And if it's too big, it can kind of diverge. If it's too big, you can also get this kind of zigzag pattern. And somebody said that Harry Potter's lightning scar, but whatever it is, you can have these different things. And ideally, you get something that's not too big but not too slow. If it's too small, it's going to converge super slowly. You got to do like thousands or millions of iterations for it to converge. Okay, and we don't want that either. So anyway, that's how gradient descent works. All right, so let's talk neural networks, okay? I have these 2 playlists that you got to watch, okay? They're both really good. Both of these channels, so I love YouTube. I probably spend way too much time on YouTube. I don't know. I imagine you guys are on YouTube a lot also. I don't know. It's just like what you do on the internet, right? So anyway, I like to watch these math and science channels. I don't know if that's a huge surprise to you guys, but But anyway, subscribe to these channels, Welch Labs and 3 Blue 1 Brown. And 3 Blue 1 Brown has excellent video on neural networks. And I'm going to follow, at least in this course, I'm going to follow the examples set forth in the Welch Labs neural networks playlist. Okay, so Welch Labs has a playlist on neural networks, and it's really cool. And I'm going to follow his example here. Okay, so you know he kind of talks through everything, and that's what we have. Okay, so you know, as far as this class goes, you can take an entire course on neural networks. Okay, you can dedicate your whole life to researching and developing better neural networks. We're going to spend like a week and a half on it, and we're only going to look at the simplest kind of a neural network. Okay, the simplest neural network. Neural networks have technically been around since the 1970s and 1980s, so that's like 40, 50 years now. Okay. But they've gained a lot of popularity in, I would say, the last 10 years, okay? And that's because the computing technology and the computing power has really allowed us to make, you know, more complex neural networks with lots of layers, lots of different abilities, and they are now pretty much a ton of AI is powered by neural networks. Okay, so you've got image recognition and different AI technologies, and those are powered by neural networks. Okay, this I'm not sure. You guys, how old are you? And I'm trying to think how old were you when the iPhone came out? You would have been like 7. Okay, I was an adult, but but basically, your phones these days pack so much computing power, right? You can take a picture of an object and your phone will be able to like label it, okay? And maybe it doesn't happen in your phone, maybe it happens in the cloud, but you take pictures, it's gonna start like your Photos applications starts applying tags and labels to them. So later on you can say like, show me pictures of dogs, and it's gonna pull up all the pictures that you took of dogs. It's not, and it's all doing this via some kind of computer. It's not like a human is looking through your photos and saying, oh, that's a dog and I better label it dog, okay? It's just happening, the computer's doing this, right? So how is a computer able to label this? Well, it's almost certainly it's being done with a neural network, okay? We're not gonna get anything that fancy, okay? We're gonna look at the simplest version of a neural network, okay? And we'll apply it to like the simplest image data set around, and we'll do that. We're not going to get to label dogs and stuff, but I think they're really cool. They're a good application of gradient descent. Also forces you to work with matrices. So all sorts of pluses in my book here. Okay. All right. So what is a neural network? Okay. In an overly simplistic sense, a neural network is how we should design a function, okay? And what is a function? A function takes inputs, does stuff to it, creates an output, okay? That's all a function does, right? You have an input value, it does something to it inside the function, and then it sends an output, okay? And that's all the neural network is, okay? The inspiration for how we design this function, okay, is it's designed, it's inspired by the brain, okay? And so inside your human brain or any kind of animal brain, there are neurons, and each neuron is connected to a bunch of other neurons via like these synapses, right? You've got these synapses that, you know, you got this neuron looking, funny looking cell, and it has these things, these dendrites, and I don't know all of the labels, but anybody in neuroscience, I don't know, you can chime in with all of this stuff, right? So the cells are connected to all of these other things, and what happens is a neuron, okay, when you see something, when you think of something, when you want to say something, you know, a particular neuron receives an input signal, okay, and then depending on the signal that it receives, it's going to either activate and shoot off another signal, okay, to other neurons nearby, or whatever. And so when you want to move your hand, your brain is saying it's shooting all of these electric pulses, and one of them is going to your arm, the muscles in your arm that says, hey, activate and move, okay? But what we're going to do is we're going to do like a computer version of this, an artificial neural network, okay? And that's going to consist of nodes. The nodes receive input values. The node maybe, depending on the input value, it will do some kind of activation, and then it creates a new output value, and it sends the output value to other nodes. Okay, so that's what we're going to do. I'm going to follow an example from Welch Labs, and our input matrix has two columns, okay? Our input matrix has two inputs, okay? And what we're going to do is we're going to try to take how many hours someone sleeps, how many hours they spent studying, and we're going to try to predict an exam score, okay? So our function takes two values in, it does stuff to it, and it creates one output value, okay? And so right now my input matrix is n by 3. I've got n observations, okay? I'm sorry, n by 2. I've got n observations, okay? Each observation has two input values, okay? So our first observation is 3 hours of sleep, 5 hours of study, okay? And then the actual value is, for the exam score, is 75, okay? The next observation, 5 hours of sleep, 1 hour of study. The exam score that came out is 82. The last one, 10 hours of sleep, 2 hours of study, and the exam score is 93, okay? Now we could have more observations. Here we're gonna have n is equal to 3, but this n could be anything, okay? What's fixed is how many inputs I have. I've got 2, okay? These are my 2 variables, and I've got 1 output. How many dimensions in my output? I've got 1 column, okay? I could tack on more observations by increasing my n, okay? But I can't really increase, you know, right now I only have kind of 2 input variables. Okay, and so so what we're gonna do is when we set up our neural network, okay, all neural networks start off with an input layer, and it ends with an output layer, okay? And so our input layer, because we have 2 variables or 2 columns in X, we've got hours of sleep and hours of study, we're gonna have 2 nodes in our input layer, okay? So the first layer, our input layer, has 2 nodes, one for hours of sleep, one for hours of study, okay? Then we've got stuff inside in this hidden layer, okay? And then the output layer will have 1 node, the exam score, okay? That's the output layer, only 1 node, okay? And what makes it a neural network is you have in between the input and the output is you have what's called hidden layers, okay? And so for our example, we're gonna just have 1 hidden layer. And to keep it simple, we're gonna only have 3 nodes in the hidden layer, okay? But you can have more than 1 hidden layer. You can have more than 3 nodes in the hidden layer. This is just an arbitrary choice, probably just to keep things simple, okay? So, so I'm gonna have 2 in the input layer, 3 nodes in the hidden layer, 1 node in the output layer, okay? And what we have is every node in one layer is connected to every node in the next layer, okay? So the diagram looks like this. I've got 2 nodes in my input layer, hours of sleep, hours of study. I arbitrarily have 3 nodes in my hidden layer. You could pick 4 nodes, 5 nodes, 100 nodes if you want, okay? And I arbitrarily only just have 1 hidden layer, okay? You could have 5 hidden layers, 100 hidden layers, however many hidden layers you want, okay? I'm just trying to keep things simple for our simple example here, okay? So I got 2 nodes in my input layer, 3 nodes in my hidden layer, and 1 node in my output layer, okay? And this is what it looks like, okay? So my inputs, I got 2, x1 and x2, those are hours of sleep and hours of study. Stuff happens in the hidden layer. And then the output layer, this is gonna be the exam score. That's gonna create a value that it predicts, y hat, all right? So this is what I've got, okay? I don't know if you heard of this term deep learning, okay? in our example, we have one hidden layer, but like I said, you can have a lot more than one hidden layer. You can have like hundreds of hidden layers, right? And if you have a lot of hidden layers, we might call this a deep neural network or a deep learning model or something like that. And deep neural networks are really, really, really powerful, okay? They can do all sorts of stuff. It's kind of, I guess, been solved now, but basically the ability for your phone to label things and say, hey, that's a picture of a dog, that's a picture of a cat, that's a picture of a car, and things like that, that has come out of the result of the work done with this thing called ImageNet, okay? So ImageNet is a data set with 14 million images, and each of these images is labeled with one of like 1,000 possible labels, okay? And so if you think of like 1,000 categorical labels, it's like they're like really really specific. So it's not just cat and dog, but it'll be like, this is a greyhound, and this one's a beagle, and this one's I don't know, you know, it's got like all sorts of breeds of dog, and then it's got like, this is a car and a truck and a tractor, and I don't know, all sorts of different objects, and they're all labeled. It was actually quite a quite a engineering task just to get the 14 million images labeled, okay? And 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 they would just give it to a computer, and they would ask the computer to label these things. And in the beginning, the computer did terrible. The computer was not able to label the images correctly, okay? It had a very high error rate. But I guess it's already been 5 years, but I remember when this was like big news when this happened, okay? That a convolutional neural network was able to pass the human error rate for labeling images, right? So even if you ask a human to label tasks or label the images, because there's like 1,000 categories, the human would achieve maybe like 95, 96% accuracy, just because sometimes they would pick the wrong one out of things that were kind of similar, okay? So, you know, you think like, oh, I can look at a picture and I can figure out which category it belongs to. And you're right, you do well, okay? But you're gonna make a few mistakes because there's 1,000 categories to pick from. You're gonna make a couple mistakes, okay? And in 2015, the computer was able to beat the human, okay? And since then, the computer has just gotten better and better and better, okay? Here is a little video of what you can do with a neural network, actually. And so let me pull up. So this is kind of showing a little bit of like what's being done with neural networks today, in that like self-driving cars, all of those things, the recognition systems there is being done with a neural network, okay? This is called the mask, I want to say RCNN, what is RC? Okay, we have a commercial first. Okay, all right, so here we go. RCNN, some kind of neural network here. I guess this is already a couple years old, but the video is coming in. This is, you know, a car driving down the street, and as the car is driving, I hope you guys are able to see this. It is labeling the different objects that it sees on the screen. Okay, so it's saying this is a bus over here. These green things over here are buses or transport. These blue things are cars. Okay, and then these orange blobs are persons, and it even labels this thing down here as a bag. Up here, it's labeling these as traffic lights. Okay, this is a and you know, as it's driving along, it's labeling each of these different things. Okay, so here's traffic light, car, and it's doing this real time as the vehicle is driving. Okay, and so this is powered by a neural network. It's just it's seeing the images as different just pixel inputs. Okay, so the input is probably 1080p video or something like that, and then it's sending out, running through the neural network, creating these outputs of basically labeling which parts of the image are part of different things. Okay, we're not going to get anything fancy here. Okay, we've got the simplest version of a neural network, but it's a starting point. Okay, and it's kind of neat. All right. So one thing about neural networks is that they are great. They are really good at predicting values. Okay, so you tell it, hey, I want to know what the outcome is going to be. It's really good for that. Okay, neural networks are terrible if you want to gain interpretability, right? Linear regression, super interpretable. You say, if x goes up by 1 unit, the output's going to change by the slope. Okay, if x2 changes by 1 unit, the output's going to change by w2 and things like that. So so you've got good interpretability for linear regression. Neural networks, you have no idea what it's doing, right? What is this node doing? Nobody knows. Okay, that's just somebody said, like in neuroscience, you can look in a brain and you say, hey, what does this neuron do? And they go, I'm not quite sure, right? We're pretty sure that this part of the brain deals with emotions and this part of the brain deals with vision and stuff, but exactly what this particular node does, we don't really know. Okay, and it's similar with neural networks. You've got all these nodes, which are basically like neurons or nodes, and you don't know what any one of these things does in particular. Okay. All right. So anyway, this is what our neural network looks like. Okay, and we've got each node is connected to every node in the next layer, right? So x1, this node, is connected to all 3 layers, or 3 nodes in the next layer. So we've got this connection here, this connection here, this connection here. This node is also connected to all the nodes in the next layer. So there's this connection here, this connection here, and this connection down here. Okay, so all of the nodes in this layer are connected to all the nodes in this layer. Okay, and then all the nodes in this layer are connected to all the nodes in this layer. So in the output layer, there's only 1 node. Okay, you can have more than 1 node in the output layer, but right now we just have 1. And so each node is connected to the output layer. That's what we have. Okay, and so what we have is we have 6 connections from the input layer to the hidden layer. And we have 3 connections from the hidden layer to the output layer. Okay, so basically each of these arrows represents a connection. And I have a total of 9 arrows, or 9 connections. And each connection is going to get a weight, okay, a weight associated with it. And that is going to tell us how important that connection is. Okay, so if you give it a high weight, then it's basically saying that, the value over here is going to play a big role in the value in this next node. Okay, so you've got different weights associated with each connection. And when we talk about training a neural network, right, I've got to train my neural network. What does that mean? It means figuring out the weights of all of these connections. So in our case, we have 9 weights to figure out. And if you have a deep neural network, you're going to have on the order of millions or billions of connections in your deep neural network. And training is all about figuring out what is the best set of weights to use for those millions or billions of connections there. Okay. So so here I have labeled all of these connections. Okay, and so the notation, all right, the notation is everything in the first set of weights, which means going from this first layer to the second layer, we're going to call W super 1, okay? And everything going in our second set of weights, going from the second layer to the third layer, is going to be W super 2. Okay, maybe I'll zoom in a little bit. Okay, so I've got maybe that was too much. W super 1 and then W super 2 for all of these. Okay, so all of the weights in this thing are W super 1. And to indicate that it goes from the first node to the first node, this weight is going to be W super 1 sub 1, 1. Okay, there's so many superscripts and subscripts. There's all of these. It's a little unfortunate. And let me tell you, it was a pain to typeset, okay? So I make you do a little bit of typesetting with LaTeX in your homework, and you already know, like, maybe it feels like a lot of work. It was a lot of work to put these slides together. All right, so, and this next connection, going from the first node here to the second node, is gonna be W super 1, but sub 1, 2, going from the first node to the second node, okay? And then this red one, going from W super 1, and going from the first node to the third node, okay, is W super 1, indicating it's in our first set of weights, but its subscript is 1, 3, first node to third node, okay? And over here, this connection is W sub 2, 1, second node to the first node. This one from the second node to the second node is W sub 2, 2. Second node to the third node is W sub 2, 3. Okay. Similarly, we have the connections going from the second layer to the third layer. And so those are all W super 2, W super 2, W super 2. But the subscript is going to be W sub 1, 1, going from the first node to the first node. There's only one node in the output layer, so they're all going to end in sub 1. But so that we've got W sub 2, 1 from the second node to the first node, and then from the third node to the first node is going to be W sub 3, 1. All right. So we can arrange these in a matrix. Okay, so our first matrix, which we call W super 1, has all the weights from the first layer to the hidden layer. Okay, and so that has 2 rows and 3 columns. Okay, 2 rows, 1 for each node in layer 1, and 3 columns, 1 for each node in layer 2. Right, so those 6 weights get arranged like this: 2 rows, 3 columns. And the second weight matrix, which consists of these 3 connection weights, okay, is arranged in a 3 by 1 matrix. Okay, 3 rows because going in, you've got 1 for each node in layer 2, and it's got only 1 column because there's only 1 node in the final layer. So they get arranged like this. We've got 3 nodes coming in and 1 node going out, so it's going to be a 3 by 1 matrix there. Okay, how are we doing? Is this feeling okay? Give me a green check if you're feeling okay. Let me also give you the answer to our first quiz question. First quiz question is B as in boy. B as in boy. Okay, so we have a question. It says, you mentioned that the hidden layer has an arbitrary number of nodes. Is this decided by the computer depending on the complexity of the model or by the programmer? It's decided by the programmer. The programmer, the human, decides how many nodes to put in the hidden layer. So the human decides the architecture. Human decides the architecture of the neural network. Okay, the computer will determine what the weights are in the training process, but the human will determine the architecture. How many nodes, how many layers, things like that. Okay. So W super 1 and W super 2, those are our weight matrices, okay? All right, about half of you gave me green checks. I hope the other half of you are okay. Okay, oh, now it's suddenly jumped up to 3/4 of you. All right, thanks for, okay, well, I hope the last quarter of you are also okay, even though you did not give me a green check. I hope this is making sense, at least arranging these terms here. Okay, so what we're gonna do is I'm gonna explain how we go from our input values, our X values in, to the output value Y hat, okay, right? So the neural network takes input values and it's gonna make a prediction, okay? And so we wanna go from the X values in, eventually to the Y hat, the output that the neural network predicts. Okay, so what it's gonna do is we're first going to take our input matrix X, which has n observations in 2 columns, okay? Because in our situation we have two columns in our input. We have hours of sleep and hours of study, so we have 2 columns. So we're going to take that n by 2 matrix and multiply it by W, which is 2 by 3. Okay, and so those dimensions line up. And so when you do this, the result is going to be n by 3. Okay, you're going to have a Z matrix, n by 3. Basically, each observation, each of the n observations is going to have 3 values in this hidden layer, right? So one observation comes in, and you're going to have that one observation will have to have 3 values in the hidden layer for Z. Okay, so the result is going to be n by 3. Okay, and I've color coded each of these weight terms. And when you color code the weight terms, I'm hoping this helps explain how the values are created. Okay, and so I color coded these, and so we're going to get n values, n rows, and 3 columns. So Z is an n by 3. Okay. What we do is we then apply a function. Okay, this is known as an activation function. We're going to apply a function to each of these elements in here. So this is n by 3. We apply a function element-wise. So this will not change the dimensions of this matrix. So, okay, I got n by 3 values in here. Each value, I'm going to apply the same function to all of these. Okay? Now, the function can technically be anything we want. Okay, but there's been a few choices for the activation function, and classically, a popular activation function for a long time was known as the sigmoid activation function. Okay, so I'll talk about it on the next slide. Okay, but the important thing here is that I'm going to apply the function f to each element in Z, and this will create another set of values that has the exact same dimensions as Z, because we did it element-wise. We didn't do anything to change the dimensions. And we're going to call this A to kind of say these are our activated values, okay? The sigmoid activation function is basically the logistic function, okay? And so, you know, it goes from, the domain goes from negative infinity to positive infinity, but the range is going to go from 0 to 1. So if t is a very big positive number, 1 divided by 1 plus e to the negative t becomes 0 when t is very positive, a very big positive number. And so you get 1 over 1, and it's going to have a max value of 1. On the other hand, if t is a very big negative number, very, very large negative, e to the negative t is going to become this huge number, you know, approaching infinity, and you're going to have 1 divided by something approaching infinity. And so that's going to go down to 0. So the range, the output, it will go from 0 to 1, although the input space is negative infinity to positive infinity. So this is what the sigmoid activation function looks like. As you go further negative, it gets closer to 0. As you get further positive, it gets closer and closer to 1 asymptotically. And this is kind of what it looks like. It's basically the logistic function. And this was a popular function for many years. It has fallen out of favor recently, okay? It's not as popular anymore. People would actually recommend against using the sigmoid function these days. Probably the more popular one is the rectified linear unit, or known as the ReLU activation function. And there's other ones, the hyperbolic tangent and the leaky ReLU and stuff. And a lot of instructional videos, the sigmoid is still used because of kind of its classical importance. So if you watch the Welch Labs video, or not if, but when you watch the Welch Labs video and when you watch the 3 blue 1 brown videos, they both make use of the sigmoid function. Okay, and so this is what we have. All right, and so let's go back to what we've done. So what we've done so far is we've taken our input matrix X, we've multiplied it by our W1 matrix, our first set of weights, and we got an n by 3 matrix of Z's, and then, and I don't have it in this picture here, but we applied a function f to every element in that matrix of Z's, and we have an A matrix, okay, an n by 3 A matrix. And now what I'm going to do is I'm going to take those A matrices, and multiply it by the second weight matrix here, okay? So I've got the A matrix, which is n by 3. That's the result of applying the activation function to the Z matrix. The A matrix, we're going to multiply it by the W2 matrix, okay? So A is n by 3, W is 3 by 1, and that's going to give me an n by 1 matrix, which we're going to call Z super 3 to kind of indicate this is the results for our third layer. So I've got the A matrix, which is n by 3, 3 columns, and each of these is going to be multiplied by one of the weights in the second weight matrix. Okay, so you know, when you do matrix multiplication, you do this first element A11 times this first element W11, and you multiply by the second element A12 by the second element W21, and the third element A13 times the third element W31. Okay, and you add all those together, so this row times this column becomes one value. So that's going to become your first value. You do it to the second row in this column, and that gives you your second row. Okay, and so this is all one value, so this result is just n by 1. Okay, so when you do the matrix multiplication and you go across the rows and you down the column, you get an n by 1 matrix, and this is our Z matrix here. Okay, and then the last thing we're going to do is we are going to apply an activation function f to each element in that final matrix Z, and this is going to give us our y hat value. Okay, so that's how we go from our inputs x through our network to our output layer predicted value y hat. Okay, so so if we do this, we've got x times w1. All right, so in summary, this is what we have. X, which is n by 2, I multiply that by w1, and okay, so n by 2 by 2 by 3 gives me z2. And then I apply the activation function f on z2, which doesn't change its dimensions. It's still going to be an n by 3. Then I take each of these activated values, this activated value matrix, and I multiply by my second weight matrix, which is 3 by 1. Okay, and that gives me an n by 1 matrix. And then finally, I apply a function to that z3 value, and this gives me y hat. Okay, and so technically, I could just kind of build the whole sequence out. All right, and so here is x times w1. This is z, and I apply the function, and that's going to be, this is the a, and I multiply that by w2. This quantity inside here is z3, and I apply the function out there, and it's y hat. So y hat can also be summarized as f of x times w1 times w2. Okay, and so that's the summary for going from our input to our output. So to get from x to y hat, this is kind of the series of operations that we do after we figure out what our weight matrices are, weight matrix 1 and weight matrix 2. Okay, how do we feel on this? Do we feel okay? Give me a green check if you're good, or a red X if you're not, or if you've got questions, type them in the chat. Let me also give you the second answer to the quiz. Second quiz answer is also B as in boy, okay? B as in boy. So I've got second quiz answer is B as in boy. Okay. How is this then used to predict new observations? Yeah, so your new observations, whatever they are, go into your X matrix, right? So whatever your new X matrix is, you plug those into your new matrix X, and then you follow these steps, and you're going to get Y hats. Okay, so whatever your new values are, so let's say you figure out, right, you train it, and you figure out what your W1 and your W2 are. We're not going to talk about training today. We'll start talking about that on Friday. But let's say you've trained it, and so you have values for W1 and W2. You get a new observation. You say, I slept 8 hours and I studied 4 hours. What's it going to be? Okay, and you put those in, and then you kind of just follow this sequence: X times W, F on Z, A times W, F on Z, and you get Y hat. Okay. So if you watch the video, or when you watch the video, you'll notice they don't talk about anything about what's called a bias term, okay? A bias term is just basically a constant that you add to each node before you apply the activation function. So you can kind of, so it's just, so like on, when you do linear regression, you multiply x times w, but then you can also add an intercept, all right? You can also add an intercept. And a bias term is basically like adding an intercept. You're just adding a constant. It's not being multiplied by anything, or maybe it's being multiplied by 1, but you're adding that, okay? So if I add this to my picture, okay, it's basically the same picture, but now it's getting more and more crowded. But each of these nodes, we're gonna add some bias term, okay? Basically a constant, okay? We call this a bias term, right? And this bias that applies to the first node is gonna be the same for every value that goes into this first node. This bias that applies to the second node is gonna be the same for every single value to that node, and same for the third one here. Okay, so this is what it looks like when you do the matrix multiplication. All right, so I have 3 nodes here, so I'm going to have 3 bias terms, 1 bias term for each node. Okay, but it's going to be the same bias term for every single observation. So how do I take care of that? Okay, all right, so my matrix for biases, the first set of biases is going to be B1, okay? Is going to be B1, and that's going to be a 3x1 matrix, right? So I want to add this 3x1 matrix set of constants to basically every single observation here. So how do I do that? Okay, in order for the dimensionality to work out, I have to multiply this 3x1 matrix of biases by basically a column vector or column matrix of 1s, okay, which we're going to call J, right? So when I do xw, x times w, this result is a n by 3 matrix, okay? And somehow I need to get my 3x1 to conform to n by 3. So what I'm going to do is I'm going to transpose b1, okay? So I do b1 transpose, which becomes a 1 by 3 matrix. And then I'm going to multiply it by j, which is going to be an n by 1 column matrix of 1s, okay? So j times b is going to become an n by 3 matrix that I can then add to the xw matrix, okay? So I do x times w, and that gives me n by 3, and then I do j times b, which is n by 1 times 1 by 3. That's also going to be an n by 3, all right? So this is what it looks like. I've tried to illustrate this out, and I've tried to color code this, and I hope this makes sense. And if it doesn't make sense right now, take a few moments after class to look at this to make sure you understand this, okay? So when you do the matrix X, which is n by 2, and the matrix times the matrix W, which is 2 by 3, you're going to get an n by 3, okay? And what we want to do is we want to add B1 to the first element, each of the first elements. We want to add B2 to each of the second elements, and we want to add B3 to each of the third elements. And so to achieve this, okay, I've transposed B, so it's this row matrix, B 1 by 3 row matrix, and I'm multiplying it by a column of 1s. This is J. J is a column of 1s, n by 1. And so this is going to become basically an n by 3 matrix of constants that can get added. And when I do it this way, the first column will be all B1s, the second column will all be B2s, and the third column will all be B3s. And when we add this, it adds up correctly, okay? We're going to do the same thing for the second bias term, okay? The second bias term is, well, there's only one, because there's only one node in the output layer. So it's just B2, okay, or B1, B super 2 sub 1, okay? Technically, I don't need to transpose it because it's a 1 by 1, but it's possible that in the future you have an output layer with more than one node, and in that case, you would need to, you would need to transpose it, okay? So here, A times W produces an n by 1 matrix, okay? I mean, it looks like a big term, but it basically, in each of these things, we're adding 4 things together. The A times the W, the second A times the second W, and the third A times the third W. Those are all getting added together, and then we add on the bias, okay? So we add 4 terms, and this becomes one value. And so even though it looks like a long expression, it ends up just being n by 1. This is just n by 1 here, okay? All right, and so in summary, we have xw plus j times b1 transpose. It becomes z2. We apply our activation function on z2 to get a2. And then we do a2 times w2 plus j times b2 transpose, and that gives me z3. And then I apply f on z3, and that gives me y hat. Okay, so y hat, if you kind of combine everything together, y hat becomes f of xw1 plus jb1 transpose times w2 plus jb2 transpose. Okay, I know it's a mess. It's a mess, but I don't know. I hope you can work through these slides and understand each of these matrix operations to understand how we are getting our y hats. When you take an input, your inputs come in your x, you figured out your weight matrices and your bias matrices, and you do this and you get some kind of y hat value. All right. Okay, so what we're going to do next, is we're going to try to figure out what is the best W's, what are the best biases, what are the best weights and best biases to use here, right? So the way we're going to do this is we want to minimize the loss function, okay? So it's very similar to what we did for linear regression, for OLS, ordinary least squares regression. We have a loss function, and in our case, our loss function, we're going to just keep it simple. We're not going to do any regularization, any kind of lasso or ridge regression or anything. We're going to keep it simple. We're going to just use the sum of squared errors, okay? We do y minus y hat transpose times y minus y hat, okay? Now for linear regression, y hat was easy. Linear regression, y hat was just xw, okay? So our loss function used to say something like y minus xw transpose times y minus xw, okay? That's what we had a couple lectures ago, all right? The only thing that has changed, okay, between what we did for linear regression, if I can, the only thing that has changed between what we did for linear regression and what we're going to do here is that the way we calculate y hat just got a little bit more complicated, okay? It's not, for linear regression, y hat, whoops, for linear regression, y hat used to just be x times w, okay? Now it's more complicated. It's f of xw times xw1 and w2, okay? But the idea here is the same. And what we're going to do is to apply gradient descent, we're going to, what did I say? We're going to take the gradient of the loss function with respect to w, or with respect to w2, w1 or w2. We're going to take the gradient of the loss function, and we're going to just apply it iteratively so that we end up at a local min for w1 or a local min for w2, or for b1 or for b2, okay? So we're going to just, it's going to be very similar to what we did for linear regression. What gets hard is, okay, finding the gradient of this. We're going to have to use a system called back propagation to find the gradient. But then once we figure out the gradient, then we apply gradient descent. Okay, we are going to end here for today, and we'll start looking at figuring out these gradients in earnest on Friday, and we'll see you then. So please take a look at the homework and get started. And I hope you guys are doing well. Stay safe and healthy out there, and we'll see you guys on Friday.